Okay, here we are again. I wanted to welcome back to the 7th week. We actually have one more week of theory after this, and then we're going to move on with some practice tests. And those practice tests after the 8th week will be a good indicator percentage-wise of how you will do on the CET exam. So if you get a 75 or above on these practice exams that are coming up, not today, not next week, but coming up, I got to figure out a way how to get them to you. They're pretty long. They're like 12 pages, so I don't know if I can send them to you as a link or if I can make hard copies and maybe send them to you in the mail or something. I have to figure that out. I'm still thinking about it. Some of you are actually on site here for your regular electronics, and I can give it to you that night, but others, I was looking at the schedules, like some of you that were in the gasoline, it looks like you're already done with your classes already. Just curious. Okay, so let's move on. Today's discussion is about digital. And let's go ahead and just move on. Hopefully you have your activity sheets with you. And we'll get moving on with this and not waste any time. So let's talk about digital electronics and what you need to know. The most fundamental concepts of digital electronics. To be or not to be. How about that? That's pretty cool. You got two B's coming in there. You got an OR gate and a NOT gate and two B's. So to be or not to be. I thought that was pretty hilarious. Okay, let's talk about digital number systems. What two digits are used in binary base 2? Well, there's only a 1 and a 0. A 1 and a 0. Those are the only two digits. You can't have the number 2 because that would be 3 digits. A 0 is one of the digits and a 1 is the other digit. There's 2 of them. Now, what are the place values for the different, the 8 places of the binary number system? Well, here's how it works. For any number system, there's always the ones place over here on the far right. Any number system has a ones place. And then whatever the number system is, you multiply each column by that number system number. Well, base 2 is a number system in this number system. So 1 times 2 is 2. And then 2 times 2 is 4. That would be the third place over. 4 times 2 is 8. 8 times 2 is 16. Times 2 is 32. 64, 128. So that's how you do it for any number system. And quite often when you're working on these number systems, you have to do conversions back and forth. And when you do conversions back and forth, you're going to have to write out these place values and put the numbers in those place values to figure things out. Okay, how do you convert the decimal number into binary? Well, here's how you do it. Say that I have a big number, such as 164 right here. I want to convert 164 into binary. Well, I look at all my place values. I write out all my place values up to, usually you want to go beyond. The next place value beyond this would be what? Wouldn't it be, what's 128 times 2? Huh? What would that be? Well, 128, that would be 16, 56, so that would be 256? Because 256 is 2 times 128, I believe. So when I draw out these place values in digital, I'm going increasing amounts from right to left with newer place values, bigger ones, and I go to the place value that is bigger than the number that I have to start with. In this case, I'm starting with 164. So I can't take any quantities of 256 out of 164. So I have to start with 128. Now, I take out one of the 128s. So I start with 164 here, and I subtract 128. That's one place value. And so I'll put a 1 in there for that place value. So a 1 in there for 128. Now I subtract the 128 from that number, and what's left? 36 is left. Then I look at the next place value here. Can I take 64 out of 36? I can't. And so I have to put a 0 in there because I can't have any of the 64s. Now, I go to the next number place. What's the next number place down? Well, here it's 32. Can I take 32 out of 36? I can. So I subtract 1 out, and then I put a 1 in that place. Right there, a 1. I subtract the 32 out, and I'm left with what? I'm left with 4. Here's 4. Now, I look at my next place value. Can I get 16 out of 4? No, I cannot. Put that in there. Can I get 8 out of 4? No, I can't. Can I get 4 out of 4? Well, I can. I can get 1 of those out. So I put a 1 in there, and I subtract the 4 out. What ends up as being 0. Now, if there were more after that, I would still have to work with the 2 in the 1's place. But because there's no 2's or 1's left, I put a 0 in there for each one. So the number I end up having here is a 1, 0, 1, 0, 0, 1, 0, 0. I have to fill in all the place values to the right of where I started. And that's how I would convert into a base 2. Okay, let's move on here. How do you convert binary base 2 into decimal? Well, it's exactly the opposite. First, I write down the place values that I have here, all the way out, for every number that I have. So if I had this number, 1, 0, 0, 1, 1, 0, 1, 1, I write that in order in the place values. And what do those numbers tell me? They tell me how many of each of this quantity that I have. I have one of the 128s right there. I don't have any 64s or 32s, but I have a 16 and an 8. And then none of the 4s, and I have one of the group of 2 and one of the group of 1, and I write those down. And all I do is I add those all together, and that would give me the base 2 conversion into base 10. So by using this digital number system here and looking at the place values, I just write down each value where I have the 1s, and I just add them all together. Now, what if I convert 0, 1, 1, 0 into binary? Well, write the place values down first. The 1, the 2, 2 times 2 is 4, 4 times 2 is 8. Those are my place values here. Then write down the binary number underneath it, 0, 1, 1, 0. How many groups of 8 do I have? None. How many groups of 4 do I have? 1. So I write down the 4. How many groups of 2 do I have? I have 1, so I write it down. How many groups of 1 do I have? None. I just add 4 plus 2, and that gives me 6. Now, how do I add together base 2 binary numbers? Well, these are the basic rules right here. These are the basic rules. A 0 plus a 0 is a 0. 1 plus 0 is a 1. 0 plus 1 is a 1. But here's where it gets tricky. Well, 1 plus 1 is 2, but there isn't a 2 in binary. So I have to go to the next place value, so I carry 1 over, like I'm carrying over the 10s in regular base 10. So 1 plus 1 is 0, carry the 1, which is 1, 0. And 1, 0 in base 2 is 2, because that's in the 2 place. So I have one group of 2 and no groups of 1, which is 2. Now here's another tricky one. Sometimes you have to carry over to another set where you already have 2 1s. In this case, 1 plus 1 is 1, 0, and then I add 1, that would be 1, 1. So quite often you run into a situation where you carry. Let's take a look at this over here. Here's a good example. 1 plus 1 is 1, 0, but I can't write the 1 in, so I carry it over here. 1 plus 0 plus 1 is 1, 0. So I have to carry the 1 over to the next place, to the 4's place. 1 plus 1 plus 1, well, 1 plus 1 is 1, 0, plus another would be 1, 1. That would actually be 3. I write down the 1 and carry the 1 over. 1 plus 1 plus 1 is 1, 1. Carry the 1 over, and there it is. So that's my answer. Now, here's something really important here. Anything with a 1 on the end is always going to be an odd number, isn't it? And if I add 2 odd numbers together, I have to get an even number. So this will help you to sift through the possible answers. You'll see that. Sometimes on the test, they'll ask you to add together 2 odd numbers, and there's only one answer that has a 0 on the end, which means that it's even. You'll see that. That'll be in the practice quiz or in the quiz. So watch for that. Let's add these two numbers together. 11011, 001101, 001101. Okay. All right. 1 plus 0. Let's see, what would that be? Well, that would be 1. I'm not carrying anything. 1 plus 1 in the 2's place. Well, that's 2, but it's 1, 0. So I write down the 0 and I carry the 1 over here. Then 1 plus 0 is 1, plus 1 would be 2, which is actually 1, 0. So I put down the 0 and carry the 1. 1 plus 1 plus 0 is 2, but that's really 1, 0 in binary. Put down the 0, carry the 1. Okay? 1 plus 1 is 1, 0, carry the 1, becomes this number here. So this would be my answer. I hope this is right. I think it is correct. 100001. Let me see here. Let me just double check. I'm doing this off the top of my head here. 1 plus 0 is 1. 1 plus 1 is 1, 0, carry the 1. 1 plus 1 is 1, 0, carry the 1. 1 plus 1 is 1, 0, carry the 1. 1 plus 1 is 1, 0, carry the 1. Okay. I think that's right. If it's not, email me, but I think that's the right answer. Okay. You also need to know a little bit about base 16. Base 16 is an interesting base system. The reason is we don't have any digits above the number 9. And base 16 actually has 16 possibilities, including the number 0. And so what do? We actually use letters. A would be 10, B would be 11, C would be 12, D would be 13, and F would be 15. So what are the digits used in base 16? Well, here they are. Here are the digits used for the decimal number equivalents. We can't use 15 for an F in base 16 because you can only have one digit in any number place. Now write out the place values for the 3 places of the base 16 hex system. Well, this is the same thing as base 2, but now it's base 16. So every number system has a ones place. To find the next place over, you multiply 1 times the base number, 16. That would be 16. And then you multiply 16 again by 16 to get 256. This would be 16 times 16. And if you wanted the next place over, even though we're not doing it here, it would be 256 times 16 for the next place value. So that's what we mean by place values for base 16. How do you convert a 2-digit hex number into a decimal? It's just like binary. Well, we know the first place value is the ones place. The second place value is 1 times 16, which would be the 16's place. Well, how many of these do I have here? I have 7 ones. So 7 times 1 is 7. Over here, this is the 16's place. But we don't know what F is. Let's see, what is F? Well, F is 15. So I have to use that. I really have a 15 in this place. So I multiply 15 times 16, and I get 240. And then what do? I just add these two numbers together. F7 really is 247 in base 10. Now, convert 2E base 16 into decimal. Okay. Well, I have 2 groups of 16. So 2 times 16 is 32. And I have E groups of 1. Well, what is E? Let's go back and see here. E is 14. So E times 14, 14 times 1 is 14. I add them together, 32 plus 14, that's 46. Here's a little bit of background for base 16 in case you're curious about it. If you ever do any research on the internet about where base 16 comes from, you're going to come across this. I thought it was quite interesting. They say that hexadecimal base 16 was invented by a magician called Mervin back in the year 700. And he was a counselor to King Charlemagne because he was born with 8 fingers on each hand. So when it came time to count the money and other things, he could count faster than other counselors to King Charlemagne, because he could count farther and quicker with 2 hands than what somebody else could do with 10 digits or 5 digits on each hand. He used more syllables and less positions, and this meant that Mervyn could express larger numbers in a smaller space. And the king thought it was magical that he could do that. He thought he was somebody really special, and he kind of was. If you have 8 fingers on a hand, you're going to be somebody special, I would presume. I just thought you'd find that pretty interesting. You don't need to know that for any kind of CET exam. Now, why is digit sometimes called binary? Well, it's called binary because you have only 2 possible states. Binary, 2 possible states. A high or a low, a true or a false, a yes or a no, a 1 and a 0, a mark and a space. What are digital gates? Well, digital gates are circuits that give you the exact same output with a given set of inputs every time. They're thought of as decision-making circuits. That's what they're thought about as. They help computers make decisions with certain inputs. What is the typical voltage associated with a high or a low? Well, a high we generally think of as being a microprocessor high around 5 volts and a low around 0 volts. And the key word here is typical, because if you've had serial communications, and if they taught you anything about serial communications, you know that serial communications actually use a positive for a 0 and a negative for a 1, which is kind of interesting. But don't go there for the CET. That's for serial industrial communications. If you ever want to learn about that, I think it's in your book. You can read about it. But anyhow, what are the 3 basic gates? Well, basic gates are the gates that all other gates are created from. They're the most simple of gates. And the 3 basic gates are shown here, the AND, the OR, and the NOT gate. The NOT gate is really easy. It's just the opposite coming out of what you put in. The AND gate, you have to have both inputs high, or 5 volts each, to get a high out. Otherwise, you don't get anything out. That's why it's called an AND. You need this and that. The OR gate is a little bit different than the AND. The OR gate is, I can have this or that to get an output. And I can see that over here. So this or that or both to get an output. So how does the AND and the OR differ? Just in the mixed states, right here. When you have a 0 and a 1 on the input. With an AND gate, you don't get an output, but with an OR gate, you will. All right, what are simple digital gates? Simple gates are created by combining basic gate circuits together. For example, a NAND gate is actually an AND gate with a NOT on the end of it. But they have a separate symbol for it. So the AND gate is exactly the opposite outputs of the NAND gate is the opposite outputs of an AND gate. N, it's the NOT of the AND, nor the NOT of the OR. So you draw the OR values and then you just exchange them over. You just change them over. So these are the NAND and the NOR. Here's the truth table. And over here, the exclusive OR. This one's a little bit tricky. You can build an exclusive OR by putting other gates together. The exclusive OR looks like this, and there's not a NOT on the end. The exclusive NOR has a NOT on the end. Now, here's interesting about the exclusive OR. The only time you get a 1 out of the exclusive OR is when you have 2 different values on the input. So you have the same inputs on both inputs, same value on both inputs. You don't get anything out. All right, now, the exclusive NOR is exactly the same as this, but it's knotted, which means it's the opposite. So the only time you get an output from an exclusive NOR is when you have 2 of the same on the inputs. Then you get an output. Anything that would be difference on the input, a 0 and a 1, you're going to get nothing out. They have to be the same. So the exclusive NOR, they have to be the same inputs to get an output. The exclusive OR, you have to have 2 different inputs to get an output. So there's the truth table for an OR. There's the truth table for a NAND. We just went over it. And that's what it looks like, NOR and an AND. Well, when I used to get confused about it, I would just draw two of them. Let me see if I can duplicate that here for you to make it, maybe I could give you a way to remember these. You have a truth table, and let's just say that it's an AND. An AND gate. Well, the possibilities are 0, 0, 0, 1, 1, 0, and 1, 1. And in an AND gate, you know the only time you're going to get an output is you have both of those on the input. So these are all zeros. That's a straight up AND. But an AND is the opposite. The NAND is exactly the same thing, but it's opposite, because you have a NOT on the end. So this would be 1, 1, 1, 0. So that was a way that I could remember which ones were which. If I had trouble remembering, I would just resort to something like that and jot it down. Here's the truth table for the exclusive OR and the exclusive NOR. We went over those. The important concept here is the only time you get a high out of an exclusive OR is when they're different on the input. The only time you get a high out of the exclusive NOR is when they're both the same. So what's the only time the output will be high on the exclusive NOR? I just want to caution you, I think I've seen the exclusive NOR, the NOR, N-O-R, 9 times out of 10, and the exclusive OR 1 time out of 10. So if I were you, I would focus in on the exclusive NOR, make sure I know that. Can gates have more than 2 inputs? Yes, they can. Look, here's a 3-input NAND gate. I can have a 10-input NAND gate if I want. What can be said about the logic inputs and outputs for gates that have more than 2 inputs? They will behave exactly the same as a 2-input gate. For example, let's back up here for a moment. If I had an AND gate, I'm only going to get an output when they're all high. So if I had a 10-input NAND, all 10 inputs would have to be high before I get an output. If I had a 10-input OR gate, I'm going to get an output if there's a 1 on any of those 10 inputs. So my point there is it's going to behave like any other gate except for the rules apply to all of the inputs. So here's a 3-input NAND. A 3-input NAND. What would that look like? Well, this is an AND gate, and this is the output of the AND right here. And how would I make this into a NAND gate? Well, I would put a dot on the end, right? I would put a NOR gate on the end. That would be represented by this dot on the end. And then if I was to go over here and draw the input for the output for the NAND gate, the 3-input NAND, what would it look like? What would be opposite of what we have for the AND gate? So my outputs here would be opposite. This would be a 1. This would be a 1. Here's a 1. 1, 1, 1, 1, and then 0 down here. So the only time I would get a 0 on the output of the 3-input NAND would be when all of them were high. So that's what they're getting at here. Draw a 3-input NAND. Well, that was an AND by itself, and here's the truth table for a 3-input AND. But if I was to convert that into a NAND, I'd put a NOT on the end of it, and it would be exactly the same as this, but opposite in polarity right there. Okay. A 3-input NAND has 2 lows and a high on the inputs. What would be the output? 2 lows and a high. Well, a regular AND would be a 0, but a 3-input NAND would be a 1. That's your answer for number 16. Okay, you're going to see these kind of things on the test. This is a very, very common diagram you'll probably see. First of all, when you look at this, when is the only time I'm going to get a high out of this? Well, what kind of gate is it? It's an AND gate, right? There's no NOT on the end. That's an AND gate. So both of these inputs have to be high for me to get a high out of this. So let's think about that. This is an and this is an and. All right, if A and B are low, so A and B are low, and this is an AND gate, what's the output of this going to be? A and B are low. Well, it's an AND gate. You have to have both of these high to get a 1 out. So I'm going to get a 0 out of this. I'm going to put a 0 into this. And nothing can be coming out of this except for a 0 because it's an AND gate. If I have a 0 on either one of these, I don't even have to evaluate this down here. The reason is, this gate up here, I know I'm putting 2 zeros in there, 2 lows. I'm going to get a low out, and any low into an AND gate makes this be low out. So my output, after it goes through the inverter, would be a high. The output for this would be a 1. And I didn't even have to do the full evaluation, just my knowledge about what was going on right here. Okay, look at the digital logic again. If A and C is low, A and C is low. Well, again, I have a low in A, and this is an AND gate, so what does the output have to be? It has to be low. A low into this AND gate makes this have to be a low. I didn't even have to evaluate this down here. A low coming out, this would have to be a high after it goes to the NOT. All right, so you see we're showing you ways to cut through doing detailed analysis by having an idea of how these gates function. All right, look at this. This is pretty interesting. Hopefully you've seen something like this. First of all, do you recognize this? Well, it's an exclusive NOR. It has a NOT on the end. Here's the truth table for the exclusive NOR. The only time you're going to get an output from this is when both inputs are the same. Now, what we have over here is a switch on a resistance. Okay. Now, let's take a look at this. Sometimes you'll see it like this. Let me draw it to you. Up here you have a positive 5. And over here on the top, sometimes you'll see a resistor. Sometimes you won't. And then there's a switch right here. That's where it means SW1. And down here is a resistor going to ground. Now you'll notice my output into the gate is right on the top resistor of the voltage divider. When I close this, I'm going to get a high voltage here. When I close the switch, this will be a high voltage. When I open this switch right here, this will be a low voltage. So when the switch is open, I'm going to get a low on the input. When the switch is closed, I'm going to have a high on the input. What you have to watch here is, they show you this diagram, but you don't know the state of these until you read the problem. So look at the circuit below. If switch 1 was to open, if this was to open right here, what would be the voltage there? If I open that, I'm going to get a low at that point. So if switch 1 opens, I'm going to have a 0 right here. But they don't say anything about switch 2. So it must be remaining closed. If switch 2 is closed, that means I have a 1 right here. So into my exclusive NOR, I have a 0 and a 1. Well, right there, 0 and a 1. That's going to be a 0 on the output. Okay. Any question on that? I hope we get that. It all revolves around this voltage divider situation here. Sometimes there's a resistor up there, sometimes there's not. Look, this one does not have a resistor in there. This one does. Do not be fooled. If there's a resistor there or not, when that switch is closed, I'm going to have a high there. When that switch is open, I'm going to have a low there. Just don't look at the schematic. Look at what they're telling you is happening in the schematic. All right, look at the circuit below. If switch 1 and switch 2 were to open, what would be the voltages here? If switch 1 open, I would have a 0 there. And if switch 2 open, I would have a 0 there. Because that would stop that 5 volts from getting down into the gate. So a 0 and a 0, I'm going to get a 1 out of there now. So my output from this would be a 1. Because both switches are going to open. Just don't look at the schematic. Look at what they're telling you. All right, there's a couple questions there on digital memory chips, and let's talk about that a little bit. First of all, what is the purpose of digital memory? Well, the purpose of digital memory is to store digital numbers. That's the purpose of it, to store digital numbers. If you learn anything about ASCII, you know that ASCII can represent letters, so you're actually storing letters as well, but you're storing a digital code. Actually, you're storing it bit by bit. So in a particular bit spot, you're going to have a high or a low, a 1 or a 0. That's the purpose of digital memory. What's the difference between volatile and non-volatile memory? Volatile memory, when the power goes away for a period of time, it goes away. The memory is erased. Non-volatile, on the other hand, does not get erased when the power is shut off. Here's an example. In your computer, you have a non-volatile memory that provides the startup sequence for your computer. When you turn the computer on, it goes to that non-volatile memory. The computer's been off the whole time, and it reads the memory, and the memory tells it what to do to load up. Another type, a CD-ROM, or a video CD. Those are non-volatile. It's always on there. It's on there all the time. A volatile memory is the kind of memory that when the power goes away, it loses the memory and it has to be reprogrammed again. So those are the two kinds. Volatile memory, for it to keep its memory, it has to be refreshed. Refreshed means you're applying a voltage to the volatile chip periodically to make it keep its memory. A lot of times we have volatile memory in our computers, and they get refreshed. Every so many milliseconds, they'll hit it with a voltage. It'll keep it fresh. Okay. Now, what does the phrase write into mean? Write into means to put memory into the chip. I'm going to put my information that I want to be stored into the chip. I'm going to store something into it. You're going to find certain kinds of chips can be stored, certain types cannot. Certain types are, let me rephrase that. Certain types are written into at the factory and you can't write over them, and certain kinds you can write into them over and over again, especially volatile memory. Now, what does RAM mean? RAM means random access memory. It's temporary, volatile memory that constantly needs refreshing. If you don't refresh it, or if the power is lost, it will erase. So RAM is volatile. You can rewrite into it over and over again, but you got to keep energy on it to keep the memory inside. If you remove the voltage, you remove the power from the chip, it will go away eventually. So what is the concept of RAM? RAM is temporary memory that I can put information in it and erase it, and put other memory in it and erase it. Just keep doing that over and over again. It's a good place to put temporary information. If you shut your computer off, generally RAM goes away unless you have a battery in there or something. What does ROM stand for? ROM is non-volatile. RAM was volatile. ROM, read-only memory, memory that's programmed into the chip and normally does not get lost, even if power is removed. So the concept of ROM is that it's non-volatile. We put information in it and it stays in there forever, for the most part. So ROM. ROM is difficult to write into. RAM is not. RAM, you can write into it easy, but you lose the information right away if the power goes away. ROM quite often comes programmed from the factory. Now, you're going to learn there's different kinds of ROM. What is the difference between ROM, EEPROM, and double EEPROM or double EEPROM? Well, here's the difference. ROM, or programmable read-only memory, which is typically the same thing, these are programmed at the factory. It's permanent memory that is programmed at the factory and cannot be changed. It's only programmable once. Your computer chip that starts up your computer is a ROM. You never want that to be erased because you want it to start up every time. If you accidentally erase the ROM, your computer wouldn't start. You don't want to do that. So ROM is actually a short form for PROM, which means programmable at the factory ROM. Now, you'll hear some people say there is a difference between PROM and ROM. Well, there is a little bit. PROM sometimes, if you are a company, you can buy a ROM chip and program it yourself, so they'll call it a PROM. Sometimes you buy the chip from the fact it's already programmed. It just depends on who you designate as the factory. So you cannot write into a ROM. It comes pre-programmed. Compared to a RAM, you can write into it. Now, to make ROM a little bit easier to handle for smaller companies, they've actually come up with two other types of ROM. EEPROM. EEPROM is an erasable ROM, and it's identified by this little window here in the chip. Usually this window is covered up with a piece of paper. And if I have a piece of paper over top of that, that chip will never be erased. So once I program it, it'll remain acting like a ROM. But if I peel this piece of paper or cover off of there and shine a certain kind of light in there, I can reprogram it. It's said to be erasable. Here's an example. In a control system, I might have a set point of 100 degrees. And I want something to turn on above 100 degrees and shut off below 100 degrees. Or vice versa. Let's say the set point is 100. Now, I might want to change the set point to 120. So I'll peel this paper off the top and shine light in there and reprogram it to be 120, then cover it back up. But it's still ROM. It can't be erased unless I erase it with that special light that shines in the window. So typically, an EEPROM can be identified with this little window on the top. Now, an even better one that's a little bit easier to erase and reprogram is a double EEPROM, electrically erasable. So I can reprogram it, but I have to apply a voltage to one of the pins of the chip. So if I hold that certain voltage on a pin, I can reprogram it and change the set point, for example. But anyhow, that is the difference between the different kinds of ROM. ROM is considered very difficult to write into or to store memory in. Basic ROM, you cannot change it. EEPROM, you can change it with special equipment. Same thing with double EEPROM. Double EEPROM, you need a special electrical signal on a pin to erase it and reset it. But they're all read-only, meaning they're normally not changed under normal circumstances. Here's your family layout of these different kind of chips. All memory is RAM or ROM. And here's the different kinds of ROM that we've been talking about here. And over here, mask ROM is the same as ROM. Okay, RAM has different kinds of RAM. These are all volatile memory, and these are all non-volatile memory. These are difficult to write into. These are not. Now you're going to say, well, Flash can be. It is easy to write into. This one can be erased and written back into, but it's considered to be a ROM because once you even remove power, like in your stick that you keep, you have a flash drive, it'll keep that memory even without power on it. Okay, are you ready for the practice quiz? That one went pretty quick today compared to last week, huh? Last week was pretty rough. All right, here we go. Look at the circuit below. If A and B are low and C and D are high, what would the output from the gate be? This is all considered one big gate, all of it. It's a combinational gate. Well, a 1 here and a 1 here is going to give me a 0 on the output. A 0 in there. A 1 here and a 1 here, if I have a low in A and B, that's going to give me a 0. So 2 zeros in an AND gate give me a 0 on the output, and I'm going to get a high. So my answer here would be what? My answer here would be high. Look at the circuit below. Look at this next one. If switch 1 were to open, what would be the output of this gate? Well, what is this? This is an exclusive NOR, right? What can you tell me about the exclusive NOR? Do you remember that? Exclusive NOR? Let me see. Can I remember that? There it is, the exclusive NOR. The only time I'm going to get a high out of the exclusive NOR is if they're both the same, so I got to remember that. Okay, so let's look at that. I need two of the same to get a high on the output. So if S1 was to open, I would have a 0 here. They didn't say nothing about this one. That one must be still close. I'm going to have a 1 there, a 0 here, and a 1 there. I'm going to get a low on the output. It's an exclusive NOR. So the answer for that would be B, low. Okay, which of these gates is a NOT? Oh, this is too easy. A NOT has one input and one output. This B would be a NOT. Don't forget, you shall not miss the easy ones. The easy ones are what's going to help you to pass. If you blow through this and answer the wrong answer, that's an easy one that you just threw away. Okay, what is the binary number for the decimal number 6? Well, I have to think to myself, the number 6. What are the place values? What are the place values? Okay, 1's place. 1 times 2 is 2. 2 times 2 is 4. 4 times 4 is 8. Okay, these are the place values. Now, can I get a group of 8 out of 6? No. Can I get a group of 4 out of 6? Yeah, 1. So 6 minus 4, that's 2 left. So can I get a group of 2 out of what's remaining? Yes, 1. Subtract 2, then I have a 0 left. Any 1s left? No. Well, 6 is an even number, and even numbers end with a 0. So 0, 1, 1, 0. Do I have an answer here for that? Yes, right here. 0, 1, 1, 0. All right, which of these gates are an AND? Does it say AND, or does it say, oh, McNeil, you didn't read it close enough. It's not an AND. I could have misread this and automatically answered that. But I'm going back and I'm reading closer. It's a NAND. Which one of these are a NAND? It would have to be C. C is your NAND. Hexadecimal 3E would be what decimal number? Well, let's see. Write down your place values for base 16. You got a 1's place, and 1 times 16 is 16, so I have a 16's place and a 1's place. Well, I have 3 groups of 16, so I have to do 3 times 16 first. Okay, what is 3 times 16? Do I need a calculator for that? Well, let's see, can we do that in my head? 3 times 6 is 18. Okay, 3 times 1 is 3, carry the 1, 48. I'm not done yet, though. See, there's an answer there. It looks like it's the good one. Nope. I have how many in the 1's place? In the 1's place, I have E. Well, what is E? Do you remember what the letter E is? Well, 10 is A, 11 is B, 12 is C, and 13 is E. Is that right? Does that make any sense? Let's go back and check. I have it back here someplace. Oh, pass it up. Did I pass it up? No. Okay. Oh, E is 14. A is 10. B is 11. C is 12. E is 14. E is 14. It's not 13, huh? I made a mistake there. Okay. So E is 14. So 48 plus 14, what's that going to be? Let's see, 8, 9, 10, 11, 12, 4, 5, 6, 62. So my only good answer is 62. You know, sometimes if you use process elimination on these, I'll show you an easier way. I already know it's 3 times 16 because of the place in here. 3 groups of 16. So it's going to be greater than 48. And the only other answer that's greater than 48 is 62. Like this next one here. Look at this next one. Use process of elimination to help you solve these. When I add two ones together on the end, just work with the ones place. 1 plus 1 is 2. And 2 is a what in binary? 2 is a 1, 0. So a 1, any number that ends in 1 is odd. These are two odd numbers. When I add two odd numbers together, I'm going to get an even number, and an even number always have a 0 on the end. Look at these. Are there any other numbers here? Which one here has a 0 on the end without even doing the math? Well, the only one that has a 0 on the end is this one. This has to be the answer. The rest of these have 1s on the end. They're not good answers. Look at the circuit below. Switch 1 and switch 2 were to open. Well, I see it's an exclusive NOR. And I know with an exclusive NOR, two of the same inputs, 0 and 0, that's going to give me a 1 on the output. So the output from this would be a high. Look at the circuit below. A and C are low. Well, A is a 0. This is an AND gate. This has to be a 0. 0 coming in is going to give me a 0 coming out. I don't care what's going on down here. This has to be a 1. So the answer for this would be a high. All right, regarding PCs and microprocessors, what does RAM mean? Can you answer this one? Which one of these means RAM? Here's a tricky one. Look at this. This is called a distractor. This looks like a good answer. Forced memory data storage procedure. Well, doggone, it might be a memory storage procedure, but what does RAM mean? It actually means random access memory. Watch for distractors that sound good. My recommendation to you about answers that sound good but you've never heard them before, don't use those answers. They're purposely there to trick you. Okay. Well, that's it. It's a pretty short one this time. And you should know the procedure by now. I will put up information a little bit later as the week goes on. On Friday, I'll turn the quiz on. You'll do it. Try to get it done before 12 o'clock Monday. And we'll have one more, actually, theory video. And we'll probably have, what I'll probably do is get you the practice quizzes, the practice tests. You should be, if you're thinking about taking the CET, you should have created a test bank of quizzes and practice quizzes with a 3-ring binder. Circle the ones you don't know and study those, and once you know them, cross them off. You're actually trying to master every possible question in the test bank. Some of them will be exactly the same. Many of them will not be the same. Some will be the same except for different numbers in them or a different gate or whatever. So there is a pretty good percentage of some that are the same. So keep that in mind. Now I'm actually looking for suggestions. What will be the best night for the CET? I know some of you are already done with your classes. I think you're on ground classes. So probably you're quite flexible. I was thinking about doing it on the 5th of October. But I know at this point, some of you have class that night. I'm talking with Mr. Kondzierski to see what he's doing that night. He's upstairs right now, and maybe I will talk with him about it and see what he says. So if you have a suggestion for a night that you think everybody can be here to take the CET, let me know. Shoot me a little memo there, and I'll see if I can work it out. But right now, I'm shooting for the 5th, but that might not be a good night because I know that Mr. Kondzierski has class that night, but I'm hoping maybe those of you that are going to take the CET will be done with your classwork by then, and maybe just have a final or something that night. You could take the CET later in the evening or even before it. So that's it for today, and I appreciate you coming. And even if you're not taking the CET, this is a pretty good review of your most basic concepts. I believe next week we're going to follow up with odds and ends of things that aren't really in any particular area, maybe testing and stuff like that. But let me take a look. Maybe there's 2 more to go, but I think there's only 1 more. We call it the odds and ends discussion, so I'm pretty sure that's where we're going with that. Okay, other than that, that's it for today, tonight, or this morning, whatever you're looking at this. And hopefully you're moving along. Thank you very much.